Should I stand here?
Yeah, no, you can, whether you wish to.
Okay.
I think they will give you a presenter. Presenter is there?
Yes.
Yes. Yeah, so welcome. We have with us today Professor Sunitha Sarawagi. She is a professor at IIT Bombay. I think the detailed introduction will be done by Dr. Nagaratna. But just now, madam, when we entered, I think we got a good news that the claim project is now approved.
Wonderful. Congratulations. Yeah.
And you were the reviewer for that in the part of the DG. So
Right, yes.
thank you very much for
Yes.
your feedbacks and other things. Now it has come out. Okay. So I request Dr. Nagaratna for the introduction.
So good morning everyone. It's my great pleasure to introduce our distinguished speaker today, Professor Sunitha from the Department of Computer Science and Engineering at IIT Bombay. Professor Sunitha completed her undergraduate studies at IIT Kharagpur and went on to earn her master's and PhD from the University of California, Berkeley. Before joining IIT Bombay, she worked as a research scientist at IBM Almaden's Research Center. She has also held prestigious visiting positions, including visiting professor at CMU Pittsburgh and visiting scientist at Google Lab. Her contributions to the field have been widely recognized. She is a recipient of several notable honors, including the Infosys Science Foundation Award, the Distinguished Alumni Award from IIT Kharagpur, and the H.H. Mathur Award for Excellence in Applied Sciences. With numerous patents and publications in top-tier machine learning conferences and journals, Professor Sunitha's research spans machine learning, data analytics, sequence models for time and text series, domain adaptation, and human-in-the-loop learning. Ma'am, we are truly honored to have you with us today to share your insights on advances in generative AI for language and structured data. Without further ado, ma'am, the floor is yours. Please.
Thank you very much. Thank you very much. It's a privilege to be giving a talk here. Thanks. So first, a disclaimer. So you got the claim project, now I'll give the disclaimer. So this visit was planned in a big hurry. Only I got one day after I heard back from Dr. Patra the topics of interest to the lab to prepare my talk. So think of it as an informal sort of chit chat of the intersection between what I do and the sense I got of the activities in areas of focus of the lab. This is not like a formal keynote polished talk. So with that disclaimer, let us get started. So generative models form the brains behind the amazing feats of modern AI. So in this talk, I will be focusing on the recent research advances in generative modeling, and a lot of generative models as applied to large language models or large multimodal models is in the mainstream, and you hear about it every day. But generative models also have a huge role to play in science, in the analysis of structured data, in the analysis of time series data, and that is not much talked about in the mainstream. So my goal will be to talk about the recent research models for creating high dimensional data and sort of more focus on applications for structured data generations like time series, tabular data, so on and so forth. And please feel free to stop and ask questions, because that way we can make it more relevant. I just want to make sure that the, is this mic on? Yeah. Oh, okay. Okay, okay, yeah. So let's get started. So this is the landscape of generative AI models. 15 years back, when I used to teach a course on advanced machine learning, I covered probabilistic graphical models, of which Bayesian network is a subclass, and that is what was the underlying probabilistic model for creating a generative distribution of the data. A generative distribution is one where if you feed data to a model, you do the training, and after that you can sample more examples of that type. And Bayesian networks form the bedrock of generative models. But then deep learning came along, and then there has been a huge sort of upheaval in terms of the kind of power that you give to that generative model. So, the first successful generative model which was used extensively first for language, then even for image generation, is what are called autoregressive models, and they are the engine which are powering model large language models. Whether you are talking about ChatGPT or Gemini, underneath it, it is all an autoregressive generative model. Then in the middle, particularly for generating stuff like images where there is no natural ordering of the data that you generate, there were technologies like variational autoencoders and generative adversarial networks, or GANs, which were very popular. A lot of people used to talk about GANs. In fact, there was like a veritable GAN zoo of GAN variants. Okay? And then there was also normalizing flows. So, these things were around, but of late, like in the past 3-4 years, a new category of generative models, which are diffusion models, is what has replaced all the GANs and VAEs. And diffusion models is what powers all the stable diffusion and other AI models that you use for generating images or generating videos or short clips. These are all powered by diffusion models. There are two kinds of diffusion models. Ones which generate data in the continuous space, like you can think of an image or an audio as analog data, sort of, right, analog data. In contrast, when you think of words or categories, categorical data like tabular data, that is not in the continuous space. So, in response now, there is, like just in the last 1 year, another category of diffusion models which have now been stabilized, although conceptually they are not very different from what was done earlier for diffusion models, which were diffusion models for discrete data generation. So, in this talk I am going to talk about autoregressive models, diffusion models for continuous data generation, and diffusion models for discrete data generation. So, this is sort of the kind of schematic of what I think of when I think of like a generative model. You give any input you can think of as a prompt or whatever, and then you output a y, and the y is high dimensional, it is complex, like image, text, time series, etc. And the other property is that this generative model is not a function. It is not like for a given x there is only one correct y. So, there are many possible correct y's. So, one of the burdens of this generative model is to be also able to impose a probability distribution over the space of possible y's. Okay? So, that is why these are often thought of as probabilistic generative models, because they will, for any given y, you can even ask what is the probability or the likelihood or the normalcy of this particular y, and then we can maybe even use it for abnormality or outlier detection. Okay. So, that is the hallmark of a generative model, and for training these generative models, of course, you will need pairs of x, y, several pairs of x, y. You know that all of AI just is very, it's just impossible without data. So, you will need lots of pairs. So, for example, early days people created separate data sets for text image pairs if they wanted to do image generation, then text content, text context, code pairs if they wanted to use an LLM as a programming assistant. But now we have this giant frontier multimodal LLMs which can do all kinds of generations of y's of many different modalities, conditioned on x also of many versatile different modalities. But the less mainstream kind of generative models, which is going to be mostly the focus in this talk, but these models are important for science, is, for example, when you use a generative model to do long range time series forecasting. So, you give as input a time series, maybe with some more context as history or as input, and you are expecting a completion of that series. Or you can condition on a structured record, maybe you give as input the composition of a particular compound that you are creating, and you expect to output maybe a variant of that compound which is more likely to meet a certain property, right. So, these are examples of generative modeling in the structured world. Sorry, I am just going to silence my phone. Right. So, first let us go talk about autoregressive models as used for language generation, which is what fuels large language models. So, a property of an autoregressive model is that it generates the output token by token. Here is an example of an autoregressive model. It is used for taking as input a sequence of tokens which are maybe asking an it's an instruction or some question like please write SQL code to do certain things, and then the main generative model is a transformer model, and you all know, I guess I am assuming that all of this is sort of familiar, like you have an autoregressive transformer model which after you have given the input gives you a probability distribution over the space of possible next tokens, and now when you generate a particular output code, you sample one token from the probability distribution, and that sample token is given as input again to the transformer, and that will give you a new probability distribution over the next set of tokens, and that from there you sample another token. So, this process of token by token generation is what gives it the name autoregressive model. You sort of you give some input, you get a probability distribution over the next token, you choose a token, most likely you will choose the token which has highest probability among the set of possible tokens, and then you give that token as input and step by step do the generation. That also has a limitation, because now if you are generating a long text, you will be requiring as many steps as the number of words in your text, and that is slow. But in any case, the autoregressive model for a language generation is well understood, but nowadays the same autoregressive model is used even for time series forecasting. There are time series foundation models which have been released by many of the big companies, which do forecasting by converting a time series into first patches. So, this is a model called Times FM which has been released by Google. How many of you know or have heard about foundation models for time series forecasting? Okay, some of you. Okay. So, this one, for example, the Times FM model, I actually want to go there because this pointer is not very sensitive. So, in this model here, you have like a time series, and first if you want to call a transformer, you convert this time series into patches. So, this is one patch, this is the second patch, so on and so forth, and this whole patch is converted using a feed forward network into a vector, and then you pass it and you get a probability distribution over the next patch, and then that patch is given as input and you get a probability distribution over the next patch. So, this is how now you can use the same autoregressive model for time series forecasting, and if you train such a model on large time series corpus, for example, this Times FM model was trained on 100 billion real world time points, and once you train it on a diverse enough large data set, then you can get impressive zero shot performance on many different domains and data granularities. You do not have to, you can use it for minute by minute forecast or yearly forecasts. Okay. So, there are many other time series foundation models. So, some of the early comers were Time GPT and Lag Llama, but some of the recent high performing models are, for example, this Chronos model from Amazon Science, and Salesforce has this model called Moiroi, and these other model I am not that aware of. So, these are some of the time series foundation models which are created out of autoregressive models. Now, I will talk to you about a new autoregressive model which we used for conditional generation of tabular data, and I chose this as an example of what new things you can do when you have a basic autoregressive model available to you with any new scenario that you have to deal with. So, the problem we were working with was called more broadly algorithmic recourse, and because Dr. Patra said that you have interest in explainability, and this has also some connection with causality. Many people are interested in causal AI. So here was the problem. So this is a project we have in collaboration with State Bank of India. They want to create a credit advisory for their customers. So let's say a loan applicant comes, and that loan applicant's data, let's say we convert into a structured record, which will consist of properties of the customer, the age, the amount of money that the customer has raised, the frequency with which the customer interacts with the bank, so on and so forth. So that's like a record data of a customer. And now typically for the last 30 or more years, most banks have been using statistical machine learning model, like maybe a gradient boosted tree, to decide whether the person should be given the loan or not. Let's say a person from this, as judged by this model, has the loan declined. Now in algorithmic recourse, we want to use machine learning to not just say your loan is declined, but to provide recourse to the customer in the form of what can the customer do, so that 3 months down the road, if they reapply for the loan, it will be approved. So this is what we call as a recourse that we want to output for the customer. We want to say, like as an example, increase salary by 50K if it's under your control, pay credit card bills on time for next 3 months to get a loan. So this is what we would like to output automatically. And now, this is the recourse we want to provide. So how can you achieve such a functionality using the core generative AI technology? So the way we formally defined the problem is as follows. So the machine learning, so like a bank already has its own trained model, which has been trained on its data set of previous customers, like this, when this was the profile, the person repaid the loan, so you had gold data, and you use that to train a classifier for loan prediction. Now we want to train a recourse model. The recourse model task is as follows. You have an example X, which when subjected by the classifier H got a negative outcome Y minus. Now that example will be submitted to this recourse model that we will be training, and that recourse model will output a new profile X plus, such that when this profile is subjected by the classifier, the outcome will be positive. That is the basic definition of a recourse model, and on this a lot of papers had been written by the time we started working on this problem. But we found that many of the techniques gave rise to this proposed whatever they were calling as the recourse example, or in fact this is also used in explanation literature. This is called like the explanation, like what was the change in original X which could have caused a different outcome, right? So this was what, but we found that many of them were not representative. So we wanted to create an X plus which has a high probability of being assigned the correct class, which is the positive class, but it should also be representative. It should not be like some weird artificial profile which is unachievable. So that representativeness, that it should look typical. You should not kind of ask for unreasonable new profiles. That is what is captured by this requirement, that the probability of the generated profile X plus given among all the customers who are approved loans, it should look typical. It should not look like an outlier. This is very important, and it was ignored by most of the earlier models. And then of course it should be easy for the customer to implement that action. So the distance between the old and the new profile should be small. So with these three goals, we created this model which we are calling Generative, and we used a generative model to output this X plus. And this is different from the previous models. Sorry that the resolution is so poor, I do not understand why in this slide. So the prior models, they were formulating it as a optimization problem, and they mostly returned brittle answers, whereas our approach, we proposed a conditional generative model over recourse instances, and using that a user can generate multiple profiles and choose the most preferred one at runtime. And also we make sure that the generated profiles are representative. So how did we cast it as a generative model? So the generative model we created is an encoder decoder autoregressive models. So here first you take the negative example and you encode it using a transformer. And now the new profile will be generated by a decoder, and that is the autoregressive decoder, which will have cross attention on the encoder profile. And using this, you can again do forward sampling to generate the, suppose if there are D columns in the profile, you will be generating the T columns one by one. So this was our goal, but actually for training this model, we would need pairs of examples of x minus and x plus. But in the original bank's data, they don't have such pairs of examples. They only have customers, list of customers who repay their loans, list of customers who did not repay their loans. So, but for training this model, we need paired data. You know, how do you create this paired data? So this is where we sort of had a new, somewhat of a new innovation. So what we did is that we took our original data, and then this created from there we created two buckets, the set of customers who are predicted as being approved, denied loans and approved loans. And from there we create a sort of a pseudo distribution, which we call a Q distribution, which is obtained by pairing, doing a nearest neighbor kind of sampling, but there is some more things you have to do to make sure that it is statistically sound. So we create samples of, from using the original data, we create nearby pairs based on the user provided cost function, and that is what we use to train the recourse model. And then we found that this paper appeared in ICLR 2025. It's an international top conference, and it was sort of it was quite interesting that compared to many earlier methods, some of them were based on VAEs. I mentioned VAEs earlier. Some were based on optimization. So there are this like 7-8 methods, and we evaluated our method, which we are calling Generative for generative recourse, along three different data sets. These are publicly available data sets along 4 different metrics, like cost, how well you are able to keep it close to the original, how valid is the example, and is it an outlier or not. And so with that we found that like a combination of all these metrics, when you take into account, then our method does quite well. So because when I was sitting through the CSIR review, I found very often people were searching for new materials which satisfy certain properties, and I feel such kind of models might be helpful, right? Instead of just sort of doing a brute force search, if you can train models for generating sort of data which meet a certain requirements as predicted by a classifier, okay, it might give you better outcomes. Yeah. So I will skip this, it's required time. So, but now we will just highlight some of the limitations of autoregressive models and move on to diffusion models. So, so the autoregressive models, they of course form the bedrock of all modern AI. But still they have this problem that their token by token generation is slow. Of course, when you use the frontier models, they don't look that slow. When you type a question, they generate a long output almost instantly, and they use a lot of tricks to make the generation fast. There is something called speculative decoding. You can read papers about it. It's very interesting about how they make the generation fast by first generating a rough draft and using the big model to just correct it. Okay. So, and there are many other tricks that people use to make the generation fast, but fundamentally the model can only reason token by token. And because it is token by token generation, it's not very suitable for high dimensional data, particularly real value data like images. Okay. You cannot use an autoregressive model for generating pixel by pixel a 1024 by 1024 image, although people used to do that in the past. There was something called pixel CNN. Have any of you heard of pixel CNNs? Right, yeah. So people use such things. And the other problem with autoregressive model is when you are doing long range generation, there is a chance that you might drift, that the original prompt might be forgotten, and consistency and long range sort of harmony might be lost when you are doing token by token generation. Okay. So that is what now sets the stage for this next category of models, which are the denoising diffusion models. In a denoising diffusion model, you start from like suppose if you are trying to generate an image, then you will start from first, like this canvas of the image filled with just random data, which is noise, and then you have a model which will denoise this noise, and it will take you away from signal to something which will look like it will take you away from noise to something which will look like signal in multiple small steps. So this is this diagram here shows quite well how it denoises gradually. Okay, that's why these are called denoising diffusion models. So essentially, the way they are modeled is that you learn a p theta, which if you look at the data at noise level xt, you learn to reduce the noise by generating a version of the data at a slightly reduced level, which is xt minus 1. And this distribution is modeled as a Gaussian distribution, where the mean of that Gaussian distribution is obtained from a trainable neural network. Okay. And this is the main network. Okay. Unlike in an autoregressive model where you are generating a probability distribution over the next token, here you are generating a probability distribution over the next noise level, like you are just removing the noise slightly. And the way these diffusion models are trained is also very interesting. So unlike in VAEs, where in order to train this model, so the data at different noise level, that supervision is not given to you. During the time of training, you are just given a set of clean images, and you have to train this denoiser at all different noise levels. So the way you do during training is first you start from clean data and you just gradually add noise to create supervision for all different noise level, and then you just train this mu theta network which learns to take you in the reverse direction. So that's why a diffusion model is said to have two phases, the forward phase and the reverse denoising phase. Another new technology, for some of you young people who have joined Dr. Patra told me that there are many talented young AI/ML scientists who have joined, data scientists. So if you are curious, and perhaps if you have a background in math, you might already be very familiar with stochastic differential equations. So there is the diffusion models have strong ties to stochastic differential equations. So instead of thinking of the noising and denoising as something which happens over a discrete set of steps, like a fixed set of, like say 10-20 steps which is decided in advance, you think of this entire process as a continuous differential equation. And that is where stochastic differential equations come in handy. And then so the noising can be thought of as adding Brownian noise to data. Starting from some constant, you are constantly adding Brownian noise, and when you do the reverse, you are actually just calculating the gradient of the log of the data density. And so that is actually quite exciting, and I teach in my advanced machine learning course the relationship of stochastic differential equation to diffusion models, and many of the students are very excited about this connection. But even though whether you are using stochastic differential equations or discrete denoising, the core model, the neural network behind it is very similar. So essentially what you have to do for this network is you take, let's say, an input which has been mixed in with noise. So here is like a cat, a clean cat image mixed in with noise, and then you give to this network the data at noise level t, and also that current noise level t as input. And this neural network, here we are showing an example of a UNet. What it does, it predicts the noise that was added to the original data to obtain this noisy version. So you can think of it as signal and noise separation, right? So you are just doing disaggregation here, and basically you just, that main trick is that how do you train this model to do disaggregation, and the training is also very parallelizable, because you can just take the clean image, add different levels of noise, and just train the noise that was added. Okay. So as I said that we will be focusing on the latest generative models as applied to more scientific kind of data. So, diffusion models have also been used for tabular data generation recently. So, there is this paper in the same ICLR conference, it is the International Conference on Learning Representation, it is the premier conference on deep learning. So, there this work is from Amazon data scientists. They wrote this paper on mixed type tabular data synthesis with score based diffusion models in the latent space. So, the diffusion models, as I just presented, they operate by adding Gaussian noise to data. So, inherently they assume that your data is real valued. But suppose if you want to use such a model to generate such tabular data has integral values of age, let us say, and it has this job and marital status, education, which are categorical values. You cannot think of them as continuous values, and okay, this is continuous, but housing is again Boolean. Okay. So, how do you generate such data using a diffusion model which essentially operates by removing Gaussian noise, right. So, for that they trained a model which is a latent diffusion model. So, what they do is first they take the original categorical data and they use a transformer to convert that categorical data into continuous vectors. It is like word embeddings, but you learn these embeddings using a variational autoencoder. So, this is the encoder and this is the decoder of a variational autoencoder. You learn and then you convert all your categorical data into latent vectors, store them away, and after that you do this diffusion, the standard forward backward diffusion totally in the latent space. Okay. So, that is why it is a latent diffusion model, and this up until recently was the state of the art for generating tabular data. Even though I said that tabular data generation is not mainstream, there is a small community of people who have been applying GANs in particular. There are many different GAN based models for tabular data generation, and what this model has shown that they are significantly better than the GAN based model, and and the main thing is that the diffusion happens in the latent space. So, this is again one piece of work we did in collaboration with State Bank of India, where they wanted us to generate synthetic data for rare events. Like suppose thankfully for banks they do not have too many people who default on loans or who do not pay, so that's so now, but when they are training a classifier they need decent amount of training data even for the rare cases. And they have been, even in the statistical machine learning community, there have been methods known for training with skewed data distribution. I am sure many of you might have faced this situation where you want to train a class where for one of the class you have very few examples, and lot of techniques have been around. This is like a 30-year-old problem again. And but the bank data scientists convinced me that it makes sense to generate using deep learning techniques synthetic rare class data, because earlier I felt that how will it work in practice? I can come up with some examples of rare class, they may not necessarily be rare classes in real life, but they said that look, anyway we are currently generating synthetic rare classes through simple means, like they just take a interpolation of existing rare customers, and even that helps. These are methods called SMOT which is used for, and now they are saying that if you can improve on that, we will be happy. So, we took on this challenge and we had this piece of work on synthetic tabular data generation for imbalanced classification. And so, basically what we found is that even generative models do not perform well for the rare classes. So, discriminative models will anyway not work well, because you at the top of it you have a contrastive loss, like the majority is always compared with the minority. Whereas, when you are doing generation, there is no direct comparison of the examples of majority and minority. So, we thought maybe it should just work right off the boat, but it did not. And we found that one of the main reasons is that there is actually a huge overlap of majority examples even in the region, in that small region where there are minority examples. So, the minority examples never really have their own space. you know, there are always some majority examples who are like them, right. So that is why we found that you need to do something more. So we created a method of decluttering the boundary between majority and minority classes, and which is called overlap region detection. Detect overlapping regions and sort of reduce them, and with that we got much better results than existing methods. And I was mentioning that there are many different methods for generating synthetic data. I was talking about TabSyn, which is the diffusion based model, but there were things like CT-GAN, GAN based for tabular data, CT-GAN plus, and then then there is this transformer autoregressive model called TabDDPM. And then there is forest flow, which is also a diffusion model, and TabSyn. And in all cases, the first thing to observe is that TabSyn is much better than the GAN based model. And in all cases, what the small trick that we applied for removing examples on the boundary helped. How am I doing on time? How much? For how long? 15 minutes. Okay. Okay. So this was one piece of work. But then we wanted to extend the synthetic data generation to generating not just record data, but transactional data, which you can think of as a temporal point process. So there is like a sequence of activities, like sequence data. Okay. So we wanted so we are currently, this is work in progress, we are working on a diffusion based model for generating temporal point process data, but which also allows flexible conditioning. I will just, so here is an example of what I mean by say activity data, like say for a particular user. So like user number 49 has done a lot of activities, like what card, what amount, which, you know, so this kind of data we want to synthetically generate. So if you have the data for a particular user for now, up until now, you want to predict the activities that will happen in the next 10 days. Okay. So such kind of data we wanted to model using a diffusion model, but not just that, we wanted to support constraints, that you want to say that give me the next 10 activities, but make sure that the total amount spent over the next 10 days is no more than a certain amount, or make sure that most of the activities happen within a particular geographical areas. So these are like controls that the user might want to impose when generating data. Okay. With an LLM, you can just specify that in the input prompt, but if you are training your own custom model, how do you provide controls on the properties of the data that is being generated? So, so this is like a model that we are building for that. So first we are also doing the generation in the latent space, but now since we are generating activity data, we have to make it state based. So first let's say we have data, original data has these records with multiple columns. Then we again use the VAE encoder to convert this into continuous space. So each record just becomes a vector. But then the order of the records here becomes important. So what we do is convert a sequence of consecutive activities into a patch. So this might remind you of the times FM model, which does time series forecasting. So we created patch out of the data, and once we have a patch will consist of, like say, 4 consecutive activities, and then before this activities, whatever was the history of the previous activities also we want to encode. And now we start the diffusion model, but in the diffusion model now we have many different kinds of input. We first encode the history of the previous activity, and then patch time step, etc. Those you can ignore for now. And then we also provide as input an encoding of the constraints that the user wants. So that how you encode the constraints becomes very important, and now the denoiser is trained, conditioned on all of these things to generate the next patch of activities. And that is how we get the synthetic data. And just preliminary observations, we have to still do the full study, is that you know, the model that you have trained with a diffusion with a diffusion architecture for constraint generation, it provides much better quality data generation. Then there have been previous LSTM based methods for generating activity data. Is this model called time autodiff. We see we are doing much better than them. And nowadays people think that you can solve all of the world's problem with LLMs. So we try to use also state of the art LLMs like GPT 4.1 and Gemini 2.5 to predict completions of activities. And we found that most of the time these models cannot understand distributions. They don't understand diversity. They generate records with repeated rows. So in each individual row might look correct, but the sequence of rows don't make sense from a distributional viewpoint. Okay. And the other big problem, of course, is the cost. We should not forget that invoking an LLM for this task will require you to give your current customer data somewhere in the prompt, and then the LLM has to process this large prompt to generate the next data. Okay. So this is a big problem. So, so now we will go to diffusion models for discrete data generation. So there are these two recent papers in the public domain which you might want to follow if you want to know more about it. By the way, I will make my slides available in case you wish to write. So, so the discrete, so there are many situations where you don't want to do diffusion, of course, in the continuous space like text. Like suppose if here is an example, say this is used in the sciences, like suppose if I give you a sequence of proteins, molecules, and you want to predict the 3D structure of the molecule. So there, you know, it does not make sense to put it in the continuous space. And also you don't want to use autoregressive models, since it's difficult to assign a linear order to the outputs you have to make in a molecule. So both autoregressive models and continuous diffusion models are not appropriate for such tasks, where you want to convert a sequence of amino acids into a 3D molecular structure. So again, when we want to do use diffusion models for text generation, they will be generating text in a way which is very different from the standard word at a time generation with autoregressive model. Here is a simulation. So initially, like when the case of image, if diffusion models for images, you start with white noise. The equivalent for text would be you start with all blanks. You give to the model a blank page, okay, and say now fill it up. But when you run a diffusion model, there is no fixed order in which you fill up the page. You know, maybe in the first step it might fill up and generate some set of words which you see over here, and then in the next step it will fill up more words, and so it gradually denoises. So in the context of text, the denoising process essentially consists of converting masks or blanks into words. Okay. So, so this is one open source diffusion model called LADA, Large Language Diffusion Models. How many of you heard of this announcement of Gemini releasing a diffusion model for text data like in the last 2 weeks? Anyway, so this was announced, but that model is not in the public domain. So this is a public domain model which does large language model generation using the diffusion architecture. So if you ask a question like what is artificial intelligence, it will, sorry, okay, this is a PDF file you are showing, right? This is not the PowerPoint. Okay, so because I had some animations, right? So you missed those animations. Yeah, maybe, so you can see nicely like the way you ask a question like, oh, okay, they want to show it. This is the PPT file, right? Okay, can you open the PPT? Because there are some more animations coming, so yeah. Yeah, the one before that. Yes. So, it should maybe you will need to, okay, I need to click. No, this is not, sorry. Okay, it is not showing still. Anyway, if you asked for what is artificial intelligence, it will just fill up the words randomly. And here is, so now one problem with diffusion models is that they might lack consistency. Like just yesterday my student was saying that they are generating a formula using a diffusion model and they do not even balance brackets. So, because they were trying to do one step generation. So, you can you want to sort of figure out. So, this is in fact a problem in the open domain. I think the inference algorithm for diffusion model still requires more research. So, essentially there is there now just in the ICLR 2025 conference there was this paper called block diffusion, which tries to partly address that in very intuitive. It's basically instead of generating the entire text from all over the place in random order, you just generate it block by block. It's like a hybrid of autoregressive model and diffusion models. Okay. Similarly, for discrete data, there is like now there is for tabular data also, it makes lot more sense to just directly generate the data in the discrete space rather than convert it into the latent continuous space. And that is what this is supposed to do here also. Can you? Okay. Yeah. Right. Yes. So, here like it is generating the data starting on the categorical data, it is masked, on continuous it is random Gaussian values, and then slowly it is refining the output. Okay. So, it is just showing the process of data generation starting from the all noise to, and it is doing it all in the original space rather than converting it into the discrete space. Okay. Now, can we advance to the next slide? It is not going to the next slide. Yeah, right, sorry, I think I have, yes. So, this is their architecture. Now, it is totally in the original space, there is no VAE, you take the original data and then you apply the, you take the original data and then you add Gaussian noise to the continuous columns, and to the categorical columns you mask it with some probability, and that gives you like the noised version, and then you have this network to denoise it. Very intuitive. But we found that this model is not as fast as a version that my students are currently working on, which according to the preliminary experiments is at least a factor of 4 faster. So, we are working on this task too. So, with that I am kind of towards the end of my talk. So, just end with 2-3 slides on what next. So, even though these generative models, like whether you are talking about diffusion or autoregressive model, over the last few months one big challenge we find is steering the outputs of the models. So, like in a large language model, nowadays you can ask the model to generate outputs which conform to a particular fixed format, and you can even specify that as a grammar. Like you can say here is a context free grammar and the decoded output should be parsable as per this grammar. Such controls are possible, but suppose if you want to say generate sentences such that if this sentence is fed to a particular model that I have, like a classifier which will predict, like say the sentiment or level of formality of the sentence, that is very difficult to do both for diffusion models and for autoregressive models. So, in general, on the fly test time control or steering of the output of any of these generative AI models is an interesting area of future work. Lot of papers still exist, but the problem is not solved. Okay. Another question I have is, so like now in any organization, like think of a large organization like a bank, they have a large number of statistical models over structured data. Can we think of creating an enterprise level generative foundation model just on their data, which will do all their, which will meet all their needs, including recommendation, including classification, missing value imputation, forecasting, privacy preserving synthetic data generation, And yeah, currently it can, but can it meet the accuracy levels and more importantly the efficiency that current statistical models provide? Okay. So, that is an interesting open question. The other question is, what is the interplay or handshake between LLMs, which seem to know it all, and your private structured databases, right? So, what can LLMs do for structured data? Certainly many people use one immediate application of LLMs for structured data is if you want to query your structured data, you can do the query in natural language. There are text to SQL generators which will allow you to query, like say if you have a huge amount of data generated from some simulation of many different, spread over many different tables, many complicated columns, which earlier you might have to write large code for such, for extracting subsets of the data. Now you can use an LLM to provide a natural language source. That is the easy part, but what else can it do? So, that is something interesting to think about. Another question is, how do you integrate structured models with general purpose LLMs? Like, so now there people are working on model stitching. So, if I have an expert model on a particular task, on a particular language, can I stitch it seamlessly with an LLM so that the LLM can call the dedicated model, and it should be able to judge when to call the dedicated model and when it should be depending on its own internal learning, and to come at kind of mix them in a in a proper way. That is also a very interesting area of research. So, I will just this one I will skip because yeah. So, with that I will end with these two talks, these 2 points on future. Yes.
You were telling about the SBI case, right? So did they were able to transfer the training data in your did they try
So, they are trying it out right now, but they found that, see, that is the other thing, like I think when we as a nation, when we talk so much about large scale AI adoption, we have to think about the compute overheads. So, in academia we have these DGX servers and we were training these models on for half an hour, in half an hour. Now, when we transfer to them in their setup, they do not yet have the latest GPU across all departments.
the server, you are running a server, they will be giving training data. So does it start with a clean zero training data?
Yeah, zero training data, right.
Is there anything open for us to use?
Yeah, so actually all, of course, SBI never shares their data with us, right. So, we run it on public data. All the data sets I talked about.
No, what I am asking is the training server kind of thing, is it some open training server is available for us to use with the clean?
Right. Our code will be available in the public domain. So, this project of State Bank of India is a CSR project. So, everything that we produce there will be put in the public domain, right. I will provide the links, yes. In fact, it's so for the genre, it's there in the paper. I will double check, yes. Right.
Right. So, ma'am, as you correctly mentioned, like condition generation is very much important for science.
Right.
But from your experience, can you tell us like how much amount of data, like corresponding to each condition, how many data points or what is the quantum of
Right.
data that might be required for these conditions to get captured
Right.
precisely by the
Yes,
model?
it is a very good question. So, for the case of the temporal point process where we are generating activity data, of course, the conditions were not available to us. So, there what we did is we took the original activities and we made up conditions. So, if I give a record, then what I will do is I will sample conditions for which this record would be okay, like it is in distribution. So, we are given the y's and we synthesize x, and that actually we were surprised that it works. So, suppose I gave you this example that give me the next 10 activities, so that the total amount spent is equal to 100. So, when we are during training, when we sample a patch say of length 10, we calculate its total amount spent and we give that in the condition. So, during training that is like synthetic condition, and then the model learns to listen.
So we have to synthetically generate conditions and the corresponding.
But the synthetic condition is just summarizing the data and giving that as input. And we tried to kind of add some leeway or noise to that, that did not help much. Yeah. So you just sort of, we have a probability with which we will give a condition. Suppose if I am generating some 10 records, I will sample with probability 0.2, whether to copy over that current value in this record as a condition or not. And it learns to, it's sort of like BERT masked reconstruction, you can say. But you know, even though we train it with pairs of conditions and records where the record, where the condition is very strict, it seems to generalize. And of course, it won't exactly follow the condition, but what we say, like suppose if unconstrained generation might have only 2% of the records following that condition, with our constrained generation it might be like 40%. So, we are able to get a huge lift, but we cannot put a hard constraint, because in any case for probabilistic models, when you impose a condition, you do not want to force it to exactly follow the condition, because your condition might take your data out of distribution. If I say give me people who earn 100 lakh salary and who have not even done high school, the user can give whatever condition they want, but then it should be in distribution. So, when you output something from a generative model, when you after giving a condition, it has to be a blend of how well you meet the condition and how much you are within the original data distribution. You cannot get out of the data manifold. And that is why, you know, models, you know, I can trivially meet the condition, but then I will be giving you out of distribution examples. Yeah. But very good question, yes. Yeah. Yes. I remember you had presented also, yes, yeah.
So you have talked about that earlier sentence generation. So in that case, can we think about the explainability, because real sentence is it is unique sort of device. So like the recourse model or something we can do what
So recourse can be used for explanation. So very often people, when they ask for explainability, they want to know why was this example given a particular class and not some other class. So then the original, the actual predicted class is what we will call as the undesired class, and what class you want to reason about, you call that as a desired class, and the recourse model can tell you if the record was of this kind, then it would have been predicted, and that indirectly gives you explanation.
So we can think about it.
You can think about it, yes. Yeah. Although our goal was not explanation, but many of the methods that I listed have, you know, they have been used in the explanation literature also. Yeah. Okay.
Differentiate between explainability and interpretability.
Because some people say like I need a model which is can be interpreted. Some people say I need it explainable.
I think they are sort of similar. Yeah, similar. Yeah. Yes. Yes. Right. Yeah.
In time series analysis, is there generally what is the criteria used for deciding the batch name?
Oh, that's also a very good question.
And one more question.
Right. Yeah. And that's actually a hyperparameter. There is no good answer. Yes.
And
Yeah.
second one, how sensitive your output is to the batch name?
It's very sensitive, you can imagine that. So I don't know, you know, we you know, this Microsoft and Google papers and all, they came along. Before that, we were also trying to train our own time series foundation model, and it's just try, hit and try, you know, what works for the average case. There are no good academic answers to these questions.
So in that case, what is the need of using generative AI in solving time series where we are having many objective inputs? Because this becomes too subjective.
Yeah, but see, that is what the foundation models, you know, they claim that they work across many different data modalities and data granularities. But you know, I still feel that many of this nowadays, even academic literature, they overstate claims. So, your doubt about whether the foundation models will be really useful for you is validated by another scientist. So, there was a IBM Alliance program they have. So, there they have lot of users, and even that person he was saying that, oh, the foundation models are not very useful for us. So, take all these claims with a pinch of salt. Maybe you know what they might be useful for is if you are a small retail business, you have a limited amount of data, you do not have the resources to train your own model, then you can you can just zero shot use the model. But if you have like terabytes of data, then it is not clear whether you should then be training your own model. There are models like patch TST which gives good results, which the same architecture, but you can train it on your own data, right? Yes.
Regarding the denoising, is there any comparison between this algorithm and algorithms like using wavelets to denoise in terms of speed or how efficient?
I have not seen anybody use that. I don't know. So, you are saying wavelets for yes,
Denoising,
right.
like class.
Right. Yeah, but see here the denoising, no, it's very complicated. See here, talking about denoising a time series is very different from denoising an image. So, like when you are doing image restoration, you cannot, with you try look at the outputs of image restoration from these deep networks, they do a lot of infilling, like they contribute content of their own, right, and that you won't get with wavelets. They basically take in priors from their billions of data to figure out, okay, what does a tree look like, and if you have a partial image of a tree, they will give you a more realistic looking tree. So, they are sort of kind of cheating in some ways, right, because they are copying over knowledge from other images. Yeah.
For that purpose only they are called generative, because they generate new things.
They, so yeah, maybe not, they kind of do mixing from many different prior, ultimately it is the data, right, right, yes.
So ma'am, regarding this example you showed text generation using diffusion model. So you said that there is no particular order that text is generated.
That is the original diffusion models, yeah.
So if it is the case, then is it really looking at future context?
It can look at future context also.
Traditional LLMs don't go,
Right.
they are causal in that.
Exactly, that is a very good observation. That is one of the promise of the diffusion models. They can be good for code editing kind of situation, because they can look at future context also. For editing applications, they make a lot of sense. Yeah. Yes. Oh yeah, those questions remain. So, you cannot treat that data seriously. You can only use it maybe, say it's sort of like, okay, if you are training a gradient boosted tree for whatever, for probability of defaulting, then if you have a little bit of data augmentation on the rare class, then you will get somewhat sort of representation of that class, and it actually it helps also. I mean, frankly, I had your kind of skepticism. I said, I don't want to do this project. They said, no, this is important, please try, etc. I just gave it to my student to just try and be done in one semester. But it turned out that it actually gives big lift in accuracy.
Yeah, because for a few data this we can do the interpolation at least.
Right, right.
But when we have the huge number of
And if you have very complicated dependencies, like say suppose when you do interpolation, then you are not capturing the correlation across columns, whereas with this, ultimately maybe these models are also doing some kind of interpolation over their training data. It is just more sort of complicated interpolation than just linear interpolation. If you look at it that way, then it is not much more dangerous than what they were doing already with methods like SMOT, which just do linear interpolation. Yeah. Yes.
The comparison of general purpose LLM generation of your structured data, is this really a problem with the LLM, or it's a problem with the prompt you give to LLM, or generating your structured data? Has that comparison done at your
No, see, actually as I said, it's preliminary work, but what we did is we gave, say, in order to train the model, we are not fine tuning the LLM, right, we are just using it in the prompt. So, we have like say data of lots of customers, but in the prompt we gave data of a few of the customers, because you cannot just infinitely increase your prompt length. And then we gave the prefix of the activities of one customer for whom we want to make prediction, and we asked the model to make the prediction. You know, if you think about it, how will it work? It cannot really create a statistical model. You know, the prompt is just for instruction. It's very difficult for the LLM to kind of abstract that away into, yeah. I was not expecting it to work, but nowadays reviewers think that LLMs can solve everything. So, we just want to show them that it just does not work, yeah.
Generic question, like suppose we, like there is a case where we have sufficient data and then we are using that model to predict something, and one situation is that we have limited data and we synthesize using different technique and then predict. Then since you are doing this work, can you tell what is actually like comparison? Can you compare like in the two cases like accuracy,
Right.
like which will give better?
Right.
This
Of course, if you have real data, lots of real data, then don't even talk about synthetic data, just use your real data. Only,
cases like in like we work in defense scenario, their data, original data is not there.
yeah,
Even
then,
it is there, it's not available
right,
to us.
right.
So then we go towards synthesizing data. But like how close you will reach to the actual, that I wanted to actually
Right. Yeah. So, there is in the papers, if you read on synthetic data generation, there is a metric called machine learning efficacy, and that measures that if you use the synthetic data to train a classifier on real data, what will be the accuracy. So, the metric I presented on my slides also, that was machine learning efficacy. Yeah. So, there you can see, you know, it of course depends on how much data, how much real data was used to train the generator, because it's not like you cannot get something out of nothing. So, you have to train the generator.
some data will be there. The thing is that suppose we have synthesized data, we have predicted something, it should not be totally
Absolutely.
fake.
Right, right. So, anything you do, you have to keep aside some data for testing, and you should not also overfit on your test data, right. Very often people do not realize, they said okay, I have a test data, but then they will be trying 100 different algorithms, and on all 100 algorithms they would have been iterating over this one test data. Now, you are overfitting on, you have essentially indirectly trained on the test data also. So, you have to be very careful when you even search through algorithms using a fixed test data set. Yeah. So, you have to keep on sort of testing on new data. Yeah. Yeah, and at some points you have to invest in data labeling. Right.
Thank you, madam. I think it was a very interactive talk, and then many questions were there, so it means a lot for us, and thank you for that. But we have a interactive session maybe, but we have not much time, but we will have some maybe half an hour kind of thing left after that. Before that, I would like to thank you for agreeing to come. It started with a different context, but then again we were fortunate to have you here. So I would like to thank you for that, and then I would like to request Dr. Mutkavi to give a memento to her. Open that. In fact, there are lots of people who have joined online and then has been listening to this talk.
Okay.
Only thing that they cannot ask questions because it's just live telecast,
Oh,
so
okay.
they will not be able to ask questions.
Okay.
and it will be available in our YouTube 4PI YouTube channel. Anytime
thank
you
you.
want to again listen to it, you can go and then again listen to that.
It's nice, very nice.
Very nice.
Thanks, thanks.
You are UC Berkeley.
Yes, yeah.
You know Jaideep Srivastava?
Yes, yeah.
You know?
Yes,
He's
yes.
my classmate.
Oh, okay.
Come.
Oh, okay, okay. Okay, yes, yes.
He's in this one now.
In some universities, a faculty member.
Yeah.
Yes, yes, yeah.
In fact, the previous open talk was by Professor Srivastava. He had come here.
Okay,
He
okay.
had come here, I think 3-4 months back or something like that.
Came in December.
December, yeah. He came in December. He gave a talk on his healthcare related applications. Yes.
Yes, yeah.
So good. So thank you very much, madam.
Welcome.
I think tea is arranged. I hope so. Tea is there outside. So have that. And after that, I request all our 4PI scientists, and also if you want the NL scientists to join for just an interactive session. Not much. Basically, we wanted to our idea is basically to see the new scientists that who have joined in last 1 year kind of thing. They can talk about what they are and all, and then she can give some guidance or advices, those kind of things, so that it becomes more useful. Thank you very much for everybody who has come and then joined, and also those who have joined online. I would like to thank them very much.